Okay, so we left off last class. We've been talking about these arches. We did one example, and we want to do another example today. So what we're going to do here is we're going to do a boring. And we're going to use a round end mill. And what we want is we want this boring to have a diameter. And I'm just going to use millimeters to make it simpler on us. We want this boring to have a diameter of 24 millimeters. And on the end here, we want this to be concaved at the center by, what do we want in there? We'll go 6 millimeters. I want to know what radius mill I should use for this. So what that's saying is if this were a complete circle, what would the radius of that circle be? Now remember what we talked about yesterday was this distance here, of course, the 6, is going to be at the highest point, the furthest point away, which is going to be dead center in this span across here. So this is going to get split into 2 equal pieces of how big? Yeah, half of 24 will give us 12 millimeters each. Now if I had left myself enough room here, I'll redraw this. This is my 6 here. This is 12 and 12. This is x. And the formula I gave you yesterday is x equals 12 times 12 divided by 6. Multiply these two because they're on that same chord and divide by the 6, which is on the same chord as the x. That gives us 24. So that is saying is from here to the other side of the circle is 24 millimeters. So from that information, what is the diameter of the circle? The diameter is just this here. So it's 24 plus 6. Equals 30 millimeters. So then from that, how do I get the radius? The radius will be diameter divided by 2, 15 millimeters. So if you were using a round end mill, you'd use a 15 millimeter radius round end. Does that make sense?
Hold on, you copied it.
Okay. Another application might be if you're going to leave a channel. Move this down so there's some more room. You're going to cut a channel. This is a segment of a circle being cut into a surface of a block. Again, we need to know what the radius of this is. The width of this is going to be 30 millimeters. The depth is going to be 10 millimeters. find the radius of the tool that we're going to use for that. I'll let you give you some time to try that in your notes. See if you can get. Okay, so if I finish off this circle here, what we have is you have this across here is going to be cut in two of 15 and 15. This is 6, right? Or sorry, not 6. This is 10 right there. And this is the x we're trying to find up here. So x is equal to 15 times 15 divided by 10, which will be 22.5 millimeters. Which means our diameter will be what? 32.5. Which means our radius will be 16 1/4 millimeters, 16.25. Very good. Anybody get that all right? Good. Want to see what else you remember from yesterday then? Let's say that this is a 30-degree sector here with a radius of 20 inches. I want to find the area of this little sliver out here. I'll give you the length of this chord here in just a second. But for now, start working on finding what you can find there. So the distance across the chord, that's this length right here, is 10.3528 inches. So that should be all you need to know to find the rest of that. Where do you start on this? Okay, we're going to find the area of the sector, but to find that, we first start with the area of the circle. You're right. So pi times 20 squared, which is what? 1,256 inches squared. Then we use that to find the area of the sector. So 1256 inches squared times 30/360. Very good. Which is going to be 104.67. Very good. Inches squared. So that's the area of our sector. Now we have to find the area of the triangle and subtract it out. How are we going to find the area of that triangle? Huron's formula. So we're going to find our perimeter, which is going to be 50.3528 inches. Then we're going to find our semi-perimeter, so it's a perimeter divided by 2, so that'd be 25.1764, correct? Then our area is S times S minus A times S minus B times S minus C. So S is the 25.1764. A is 20, so I'm going to minus 20 would be 5.1764. B is also 20, so I subtract 20 would be 5.1764. And C is the 10.3528, which is going to be 14 point what? $14.8236, I believe. So then we're going to multiply that up, take the square root to get the area. per second, square root 25.1764 times 5.1764. I'm just going to square it because it's in there twice. Times 14.8236. 100. Almost exactly. Bless you. So 100 square inches. So the area of that segment is going to be the 104.67 minus 100. So 4.67 square inches. Anybody get that? Yeah. So that kind of wraps up our arcs and our circle stuff. What do you think? Not bad? Better than a sharp stick in the eye? For now? There's another shape that comes up often enough. More so in construction, but the wood construction guys take the same course, so we got to put it in here. And that is octagons. Octagon, we're talking about regular octagons, are 8-sided figures with each side the same length. So pretend that looks like a regular octagon. Close enough. So the length of the side is going to be labeled S. If I go corner to corner on the diagonal, that's called the diagonal. So we label that D. Another way to think about it is if this were a circle, that would be the diameter of the circle. And then there's distance from side to side going on the flats. From there to there. That is called the flat distance, or F. If I have any one of those dimensions, I can find the area. If I know the side, the area is equal to 4.8275 times the length of the side squared. F is for the flat.
Where'd that 4 come from?
The 4, that's just a constant that I had to give to you. So let's say you have a piece of stock and you want to create, you want to mill it down so it's an octagonal piece of stock, octagonal rod, and you want the side of it here to be 8 millimeters. What's the area of that going to be? Well, that area will be 4.8275 times 8 squared. Giving us 308.96. That was in millimeters, so that is now millimeters squared is my area. If I know the flats, I can find the area from the flats, because that area is going to be 0.8284 times the flat squared. Now the 4.8275 and the 0.8284, those are things that come from trig. Next semester, we'll see where they come from. For right now, you're just going to have to accept that they're right. So if I have an octagon, that, let's say that I have I measure it with a caliper, side to side, and I find that that distance across there is 24 millimeters. So the area of that is going to be 0.8284 times 24 squared. $477.16 millimeters squared is the area. That's the number that I had to give you. And then if we know the diagonal distance, the area is 0.7071 times the diagonal square. So let's say we know that the diagonal across here, let's say that is going to be 30 millimeters. Now where this would come in is, let's say you've got a round piece of stock, you've got a rod, and you want to mill it down to be an octagonal piece. Well, the diameter of that round piece would be 30 millimeters, and this would be the largest octagon that you could get out of that. So the area of that is going to be 0.7071 times 30 squared. $636.39 millimeters squared. This one? Well, this one was just the side. So now from this example here where I gave you, we know that this 30 millimeters is the diameter of that round stock. Let's say we want to know what the distance size, the side of this is going to be if I mill it to make the maximum sized octagon that I can. Well, the area of that maximum sized octagon we just figured to be 636.39. If I was figuring that area out from that side there, that would be S, right? That area would be 4.8284 times, oops, sorry, 8275, not 8284. 8275 times the length of that side squared. So I'm going to have to work this backwards. I'm going to take my area divided by 4.8275. Which gives me 131.8256. And then I'm going to have to square root it. So second square root of that previous answer is 11.4816 millimeters. So the length of that side is just under 11.5 millimeters, 11.4816 millimeters is what I'm getting out of that side. Does that make sense? And we haven't done solving equations yet. That's going to come up in a couple of weeks. That's basically what we did here is we solved an equation. We had all of this. We wanted to get what the S equals, so we got rid of everything else. And that's something we'll cover here in a couple of weeks. But for now, it's just a matter of working it backwards. To find the area, you would have squared S and then multiplied by 4.8275. So to work backwards, you divide by 4.8275 and square root. We won't do more than a couple examples like that. Yeah. Yeah, these constants are given. Those are in the packet that you have. In fact, yesterday I gave you a packet with circles on it. That packet, does that go up to page 170, I believe? Is it 170? I think should be the back page of that. Yep. Is 170 the last page of it? Okay. On page 170 and 169 are these formulas are there too that I just gave you. So what we just covered is on page 170 in that gray box. Do those problems. And then remember from yesterday, page 165 through 168. Also the gray boxes. Do those. There's problems there on circles.
This is on chapter 8, perimeters?
Nope, it's the next packet. There's one that it should start out with 157, I think, is the first page of the packet. Nope, that's a different one. Yeah, the front page is mostly gray.
Yeah.
Yep, there you go. That's the one.